Geothermal energy is the heat that is generated and stored deep inside the Earth. As we've learned, the Earth is made up of several layers, and the deeper down you go, the hotter it gets. For each kilometer of depth, the temperature rises by about 25 degrees Celsius. There are three main sources of heat in the Earth's interior. First is leftover heat from the formation of the Earth billions of years ago, when it first condensed from the cloud of hot gases and particles in space. Second is the heat generated by the sinking of denser materials to the center of the planet, which, like the first one, has not yet fully dissipated. And third is the heat radiated by the constant but slow decay of radioactive isotopes, which are atoms of the same element but with a different number of neutrons and therefore have an unstable nucleus, such as potassium-40 and thorium-232 within the mantle. Among these three, the decay of radioactive isotopes generates the most significant amount of heat. But how exactly do we harness this heat from the Earth to power homes and cities? Geothermal wells are drilled into the Earth's crust at shallow depths ranging from 3 to 10 kilometers. The heat can be extracted to produce electricity using a variety of methods, but is all generally done through the use of water and steam. The process for this is as follows. Hot water is pumped from reservoirs underground through a well under high pressure. When the water reaches the surface, part of it boils into steam as there is less pressure in the surface than underground. The plant has a separator that receives a mixture of steam and liquid water. It allows steam to proceed to a dryer where all traces of moisture is removed, whereas liquid water is directed to a pump that returns the fluid underground. The hot, dry steam flows through the turbine, which is connected to a current generator. The thermal energy of the steam is converted to mechanical energy, which in turn is directly converted into electrical energy. The steam that passes through the turbines is then cooled off and condensed back to water in a cooling tower, and the cooled water is then injected back into the reservoir underground to continue the cycle. It is necessary for geothermal plants to return the fluids used to generate electricity in order to maintain the reservoir pressure. There are three main types of geothermal energy plants, namely the dry steam power plant, the flash steam power plant, and the binary cycle power plant. All these make use of steam to spin the turbines to power the generator, and they only differ in terms of how they use it. For the dry steam power plant, hot steam from underground is directly connected to a turbine. For the flash steam power plant, hot water is first pumped into a flash tank, which converts some of the geofluid into steam, which powers the generator. Finally, for a binary cycle plant, hot water is pumped through a heat exchanger where it heats a second liquid, with a lower boiling point, that transforms into steam that then spins the turbine. The ideal type to use may vary depending on the temperatures of the groundwaters available in an area. Energy from less than 10 kilometers deep contains 50,000 times more energy than all the oil and natural gas resources in the world. According to Hansen, the Philippines is the home to 3 of the top 10 biggest geothermal power plants in the world. Located in the Pacific Ring of Fire, the Philippines is also the world's second largest producer of geothermal energy. The country's 3 biggest geothermal power plants are Macban Geothermal Complex in Batangas Province, Tiwi Geothermal Complex in Albay, and Maltibog Geothermal Power Station in the island of Leyte. In addition to being environmentally friendly due to its minimal impact on pollution relative to fossil fuels, it is also a reliable and consistent source of power. It is renewable and sustainable because the hot reservoirs within the Earth are naturally replenished. In a local context, the Philippines is located in a volcanically and tectonically active region, making it ideal for geothermal plants since the heat is closer to the surface and less expensive to harvest. However, we cannot ignore some of the downsides as well. For one, the upfront costs for geothermal energy production are relatively high due to the need for sophisticated equipment. It is expensive to carry out seismic sensing, test well drilling, and other necessary preliminary investigation for new geothermal plants to ensure that they can meet production requirements and standards. Another thing that limits the growth of the geothermal industry globally is that it is location restricted. Not all countries have ideal conditions for it, so the technology and usage is not as widespread as it could be. Thank you!